On number 2, as for all of 1 through 12, we are to assume that x and y are positive and use properties of logarithms to write the expression as a sum or difference of logarithms or multiples of logarithms. So basically what you want to do here is look to see if any of the 3 logarithmic properties addressed in this section apply, and since this is the logarithm of a product, we're going to use the product rule. So the product rule says that if you have the log of a product, it is the equivalent to the log of, or the sum of the logs of the factors. So your first step looks like this, but we can go a little further, because then when we see that 9 can be rewritten as, if I can write, can be rewritten as 3 squared, then we see that we can clean that up a step further, or in essence what we're doing there is reducing that log down to a 3 log instead of a 9 log. So the fact that we have an exponent says that we're going to use the power property, or the exponent property, whatever you want to call it. It just basically says that you can take the exponent off as a coefficient and it will be the same thing, which you should have addressed in the exploration as well. So your final answer is 2 times the natural log of 3 plus y. And then on number 4, we have the log of a quotient, so we apply the quotient property, which says the log of a quotient is the difference of the logs, and you take the log of the top and subtract from it the log of the bottom. And that's all we can do to that one, so it's just log 2 minus log y. On number 6, we have the log of a power, so we're going to pull that exponent, negative 2, off as a multiplier, and that's all we can do to that one, so our answer is negative 2 log base 2 of x. Number 10's got a little more going on, and this is a more typical problem you should be prepared for. We have a log 1,000 times x to the 4th. Okay, so it's a product. So your first step is to pull it apart as a sum of the logs of the factors. And then we're going to address each thing separately. Again, like we did with the 9 on the earlier problem, we're going to rewrite 10 as a power, and that is 10 to the 3rd. And then we're going to apply the power property on log x to the 4th by pulling the 4 out front. So that's 4 times the log of x. And then we can pull the 3 off as a multiplier on our first term, and we have 3 log 10 plus 4 log x. Anytime you have a number inside a log, you should look to see if the number inside that you're taking the log of is the same as the base. And remember that log without an expressed base is base 10. So log base 10 of 10 is just 1. So 3 times 1 is 3 plus 4 log x, and that is our final answer for that one. Then we go to number 12. A little uglier, but not that big of a deal. Again, it starts as a quotient, so we will apply the quotient property. And the quotient property says that the log of a quotient is the difference of the logs of the numerator and the denominator. So we have the natural log of the cube root. Let's try that again. My pen and I weren't communicating well there. Cube root of x minus the natural log of the cube root of y. And then we can rewrite each of those as a power by rewriting them this way. Which allows us to pull the 1/3 out. So we have 1/3 natural log of x minus 1/3 the natural log of y. And then we can go one final step As I've told you before, anytime you can factor something, you should. And the factored form of our final answer is 1/3 of the quantity, the natural log of x minus the natural log of y, and that is our answer. Then we go to number 14, and in this set it says that assuming that x, y, and z are positive, use properties of logarithms to write the expression as a single logarithm. So basically now we're using the properties backwards, if you want to think about it that way. So what is the sum of two logs? Well, if it's the same base, then you can rewrite that as the log, same base, of the product. So that's just log 5x. That's all you can do to that one. You know it's going to be short when you have 3 problems on one page. Then we go to number 16, which is the difference between the natural log of x and the natural log of y. And we get a difference from a quotient, so we can rewrite this as the natural log of the quotient, x over y. Then we'll look at 18. And this kind of probably already looks simplified, but remember, what does a coefficient have to do with log properties? Well, we can rewrite it without a coefficient as z to the 1/5, and z to the 1/5 is generally better written as the 5th root of z. And that is number 18. Moving right along, we get to number 22. Got a little more going on in this one as well, but it's the same set of directions, the last one in this problem, or in this problem set. So again, when you see a coefficient with a log, you want to think about rewriting it so that that coefficient becomes the exponent of what you're taking the log of. Make that square look a little more like a square. And then we'll have another square on the outside of that. Then we're going to use our exponent properties to clean up what's inside each of these logs. So if I cube x cubed, I get x to the 9th, and then y cubed plus, and we'll do the same thing over here with the square. So y squared, and then z squared squared is z to the 4th. And then now I have a sum of logs of the same base. It means that I can rewrite this as a product. So I just take down whatever's inside each. So I have x to the 9th times y cubed times y squared times z to the 4th. And then the final step is to apply my my exponent properties one last time to clean up the inside to give me the natural log of x to the 9th, y to the 5th, z to the 4th. And that is our final answer to number 22. Then on to number 24. Again, not a lot for these either because we have them together on the same page. And number 24, we are to use the change of base formula and our calculator to evaluate these. And the change of base formula, kind of the easiest way to remember that is to write the log, same base, or no, I'm sorry, we're changing base. So you have a choice. You can either change it to natural log or log base 10, and which is the reason those two are the ones you want to go to is they're more commonly used and are on like the TI-83 and other calculators with their own button. So we'll just go log base 10 and then divide that by log base 10 of the base. So it's the thing you're taking the log of on top and then the log of the base on the bottom. It's easy to remember that way as base on the bottom. And when you type that in your calculator that way, 1.8295, and yes, your Inspires will give you this answer, but I want to see this bit written out to demonstrate that you are in fact practicing the change of base formula, just so you'll have it in your repertoire for later. And I will write down here, you could also do natural log of 19 over the natural log of 5 and get the same result. So we'll put an or there. Either of those would work. Then on 32, we are to do the same thing, but this one is abstract because there's no number on the inside, but this really forces you to know the pattern. This is the equivalent of the log of c minus d over the log of 5. And there's nothing, you can't put that in your calculator because of the fact that we have the c minus d in there. And then equivalently, you could do the natural log of c minus d over the natural log of 5 and get the same result. Now, the directions here actually specified the natural log, so the second choice is better, as it turns out. I didn't pay close attention to the directions, but I do want you to realize that these would all give you the same thing, and you can play with number 24 on your calculator to verify that. And that is the last example and the end of the video.